This is the final go, no go poll for Flight 3 of Starship. Avi 2.
Go.
Stage 1.
Go.
Stage 2.
Go.
Flight directors, go for launch.
Hello and welcome to the Terran Space Academy, where we help prepare you for a bright future in the space industry. Remember to stay in touch, let us know what you like, and support us on Patreon. We appreciate you. Right now, the only human-rated American spacecraft is the SpaceX Dragon capsule. But if NASA has its way, there will soon be 3 more. On the left, you see the Boeing Starliner, and on the right is the Lockheed Martin Orion. None of these capsules have ever carried a human being back from orbit, much less the moon, which is what the Orion is uniquely designed to do. Coming back from orbit entails a re-entry velocity of 7.8 kilometers per second, while coming back from the moon requires a re-entry velocity of around 11.2 kilometers per second. About the same as Mars, by the way. America needs a deep space return vehicle, and the Orion is what we started designing back during the Constellation program as the crew exploration vehicle. Constellation was going to be America's triumphant return to the moon, no later than 2020, the politicians said. Quite often, simply announcing a prestigious goal gives a politician bragging rights, even if they never fully fund the program. This is what happened to Constellation, which was canceled in 2009. But the CEV survived as the Orion capsule. The Orion is made from aluminum lithium alloy, and it can take 4 astronauts on a journey around the moon. It has one AJ-10 hypergolic rocket engine, burning Aerozine 50 and nitrogen tetroxide. Aerozine 50 is 50% bi-mass hydrazine and 50% unsymmetric dimethylhydrazine. This gives a good combination of efficiency and storability. It also has 8 R4D11 hypergolic engines burning monomethylhydrazine and NTO for secondary propulsion, with 6 pods of reaction control engines you see here. What makes Orion unique is the advanced heat shield, shown here. This allows the Orion to survive high-speed re-entries that would destroy the Dragon, Starliner, or Dream Chaser spaceships, if it worked right. But on its only test flight around the moon so far, things didn't go completely as planned. The Orion launched on 16 November 2022 aboard the only SLS to fly so far. Once in orbit, the Orion fired its interim cryogenic propulsion stage, powered by an ultra-efficient RL-10B2, on a translunar injection burn, sending it around the moon. The Orion does not have enough propellant for a low lunar orbit, by the way, which many see as a serious flaw in its design. The mission lasted 25 days, 10 hours, and 55 minutes, traveling over 2.1 million kilometers, which is about 1.3 million miles. It came within 130 kilometers of the moon's surface. A low lunar orbit is considered below 100 kilometers, by the way, traveling out to 432,210 kilometers at apoapsis. The next flight was supposed to have already taken place in 2023. But this was moved out to 2025 when some problems on the first flight were identified. On flight day 19 of the Artemis 1 mission, Orion performed its secondary return trajectory correction burn at 10:43 a.m. using the RD-411 engines and increasing its velocity by 0.52 meters per second, which is about 1.16 miles per hour. At 12:42, the power conditioning distribution unit shut off power to some systems, with 4 of the downstream current limits switching off. Think of these just like circuit breakers in your home that make sure no power fluctuations damage equipment. The shutdown cut power to protect the propulsion and heater systems from damage. After the teams reset the system, it seemed to work fine. But there had been a previous case of one of the 8 umbilical latching current limiter units, seen here, opening without a command. An open circuit means it shut off. A closed circuit means power can travel through. The open limiter was ordered to close again, and since there is redundancy, power to avionics was not lost. Issues like these are not unexpected, but human beings are supposed to fly on the next Artemis mission. These issues will need to be resolved before that flight. And there was one more problem found with Orion. During its high-speed return from deep space on 11 December 2022, the thermal protection system, or heat shield, measuring 16.5 feet or 5 meters in diameter, the largest of its kind ever developed for human spaceflight, had worn away differently than predicted. Coming back at 40,000 kilometers per hour, we expect areas to char and ablate away, but those areas are supposed to match computer simulations and ground testing. The Orion's patterns did not, and more material had burned away than expected. This is a serious problem, as the only thing between the astronauts and certain death is that heat shield. The Orion's heat shield is made of Avcoat, the same material developed by NASA during the Apollo program, with some modifications and updated application procedures. According to Lockheed Martin, instead of having workers fill 300,000 honeycomb cells one by one with ablative materials, then heat cure the material and machine it to the proper shape, the team now manufactures Avcoat blocks that are pre-machined to fit into their positions and bonded in place on the heat shield's carbon fiber skin. This allows Avcoat to be applied in just a quarter of the previous time and saves money. But at what cost? Post-flight inspection of the Artemis 1 Orion heat shield showed an unanticipated loss of char layer pieces from the spacecraft as well as cracking of the Avcoat shield. NASA's ArcJet complex at the Ames Research Center in Silicon Valley has been studying these unexpected issues. They do this with the Laser Hardened Materials Evaluation Laboratory, which is managed by the Air Force Research Laboratory. This lab does thermal simulation testing, equipped with high-power lasers. ArcJet testing is also done on thermal protection materials, with plasma mimicking the intense heat of reentry.
So the basic operation of the ArcJet is to simulate the reentry environment. The nuts and bolts of it is you want to take gas and just take it to a very high energy level. And the heater is the workhorse of the ArcJet facility. So all the components come together to make the test work, with high pressure water cooling for the cooling of the segments, to the test gas and nitrogen and oxygen, to the electrical power, and then into the vacuum system for testing the material. Okay, so when we receive a model, typically the models come with thermocouples already attached. And then in the test chamber, we have 2 hydraulically actuated sting arms. So we would establish our flow field, and then the model is on a sting arm, be rotate into the flow, we would test it. And then we would rotate it out of the flow field. So on that sting arm is where all the data hookups are. So we would run that to our data system. During the test, we get all kinds of additional data. We would test these types of ablators, typically up to 3,000, 4,000 degrees Fahrenheit, even higher. We would test them at very high temperatures for different types of trajectories. Primarily for the lunar is what gave the highest types of heating rates and correspondingly the highest temperatures of the surface of the model. For a ISS type of reentry, the heating rates are a lot lower, so we're talking about 2,000, 3,000 degrees. But for a lunar type, very ballistic type of reentry, you're about 4,000 degrees, even higher than that.
Coming back from the moon generates a temperature of about 2,760 Celsius, which you will note is much higher than the 1,650 Celsius from orbital reentry. Lockheed Martin also organized a core team of engineers to investigate and understand the cause of the char loss and figure out what would need to be done to prevent it from happening again. The teams noted that instead of ablating smoothly, small pieces of the shield had been blasted away, in a process usually called spalling. And while temperature data inside the cabin remained at expected levels, it cannot safely be said that this is okay. If a big enough piece of the shield breaks off, it could provide an entry point to break up the shield further. Right now, the teams are seeing what changes need to be made in the application process to keep this from being a problem in the future. I say go back and do it exactly like they did in the Apollo days. It might cost a little more, but 7 out of 7 safe returns from deep space is a perfect record. Next, let's look at the Boeing Starliner spacecraft. The capabilities and problems with this ship were covered extensively in this lesson, but to update, Boeing has not been doing well lately. After the 737 MAX fiasco, where a faulty flight system crashed 2 planes, killing 346 people, it became clear that the company had developed a serious problem. There was a time when Boeing was unmatched, driving the aviation industry to higher standards of safety. and Boeing had played a prominent role in spaceflight. Boeing had started work on the X-20 Dinosaur spaceplane, and this, the first stage of the amazing Saturn V rocket, which was made by Boeing using F-1 engines by Rocketdyne. Called the S-1C, Boeing built these at the Michoud Assembly Facility in New Orleans, the same place where Lockheed Martin later built the Space Shuttle main tanks. For decades before and after the Apollo missions, Boeing had built amazing military and civilian aircraft, always putting safety through engineering ahead of all else. Top management had come up through engineering, and any worker on the line could stop the process if a problem was found. Then they were bought out by a rival company and everything changed. Engineering management was replaced by financial management, and short-term stock gains became more important than safety. But it takes time for these changes to work their way through the assembly line. In 2010, Boeing unveiled the CST-100 Starliner as a partially reusable low Earth orbit spacecraft that would provide crew and supplies to the International Space Station. The crew capsule is smaller than the Orion, with a diameter of 4.56 meters and a height of 5.03 meters. It can operate for only 60 hours in free flight, but can stay docked for 210 days. For re-entry, the Starliner uses the Boeing-designed lightweight ablator. When the Starliner is mated to an Atlas V, as it has been for its upcoming flight, there is an aeroskirt to provide aerodynamic stability and dampen shock waves. Construction on the Starliner started in 2011 at Kennedy Space Center, with the first launch scheduled for 2017. By 2016, they were running behind and moved the launch to 2018, then moved it again to 2019 or 20. In 2019, NASA paid an additional $287 million to help Boeing cover the delays. Orbital Flight Test 1 launched in December of 2019, thankfully with no crew, as the ship's computer was off by 11 hours. The ship tried to initiate an orbital insertion burn at the wrong time. This exhausted the control thrusters, and the ship had to come back to Earth without coming near the ISS.
What ended up happening is the spacecraft tried to maintain a very precise control that it normally wouldn't have tried to maintain, and it burned a lot of prop in that part of the flight. And when that prop got burnt, it looked like we weren't going to be able to go ahead and rendezvous with the International Space Station.
A review team working with NASA found 80 problems to correct, with some of these still withheld from the public as proprietary. A second orbital test flight was ordered before the ship carried crew, and a $410 million charge was taken against earnings by Boeing to cover the cost. One of the changes was a cover over the docking mechanism, similar to the one on the SpaceX Dragon. The next flight had been planned for 2020 with a crewed flight in 2021, but that flight was delayed again until the first quarter of 2021 due to software errors, moving again to August 2021. In August, the Starliner was mated to an Atlas V and readied for launch, but a ground test found that hypergolic fuel had slipped past valves and reacted with moisture in the air, corroding the valves and causing them to fail. This could not be repaired on site, and Starliner was moved back into the vertical integration facility. Repairs there also failed, and the ship had to be sent back for disassembly. Finally, repairs were completed, and the ship was ready for launch in May of 2022, launching without problems until two of the orbital maneuvering and altitude control system thrusters failed during orbital insertion. The other thrusters compensated, and with the help of RCS thrusters, the Starliner made it to the ISS this time and docked. After 3 days, the Starliner detached and landed back on Earth. Now the Starliner is rolling back out for its third launch, which is supposed to carry a crew of 3 astronauts. As of this lesson, Starliner, with a launch mass of 13,000 kilograms, has been attached to the top of an Atlas V rocket. The mission will be composed of 5 phases: pre-launch, launch, docking, undocking, and landing. The Atlas V is 58 meters tall and 3.81 meters in diameter. The first stage is powered by an RD-180 RP-1 fueled engine. Most of you will recognize this as a Russian twin-chamber model, derived from the 4-chambered RD-170. Boeing had selected the medium-lift Atlas V for the Starliner in 2011. Atlas can be equipped with solid rocket motor boosters to improve performance, using first the AJ-60A and now the GEM-63. The second stage uses the RL-10-powered Centaur. Atlas has an almost perfect 98.93% successful flight record and is human-rated, but its days are numbered. Elon Musk had called out the use of Russian rocket engines long ago as a security risk, and this time he was right. Russia's attack on Ukraine created a series of sanctions and reactions that left Russia with no funds to maintain an effective space program and the U.S. with no access to Russian rocket engines. The last ones were delivered in April 2021, and 17 launches remain. The Vulcan rocket was designed to replace the Atlas and is powered by 2 Blue Origin 3 methane-fueled engines, described here, keeping the Centaur second stage. It had its first successful flight in January of 2024 and will be carrying the Dream Chaser later, which I have always thought should have been funded over Starliner. At some point, we need to understand that while companies may be immortal, the people that make them successful and safe move on. The last flight of Starliner still had too many errors, and I for one don't think it's safe to fly with crew in May of this year. Let us know what you think, and stay safe at Astra Pro Terra. Hello, fellow space scholars. I wanted to thank you for being here. This channel started 4 years ago for many reasons. One of them is that I love to teach and have always wanted to learn how to create video lessons. Another was my frustration at the lack of facts in space news. I wanted to make sure that those truly interested in space science had somewhere to go to learn about the equations that make rockets possible, to give you the tools to make your own evaluations of different launch systems. But as important as understanding the equations are, they limit my channel to those with a serious interest in understanding space science. As many of you know, the YouTube algorithm promotes broad topics that are easy to understand. Our space science lessons, however, require a more detailed understanding, and I don't want to dumb the lessons down. But that makes the target audience a lot smaller. To take this channel to the next level will require that I invest more time and resources, and that will require your help. Therefore, I really need your support via Patreon or YouTube membership. Just a little bit every month can make a huge difference, and would be greatly appreciated. I thank you so much, dear friends of rocket technology, for your continued support, and I can't tell you how much it means to me. Thank you, and stay safe. At Astra Pro Terra.
Orion's journey to the moon began on the bayou. NASA's Michoud Assembly Facility in New Orleans is where technicians with Lockheed Martin began welding the pieces of the spacecraft's underlying aluminum structure together. 1 year later, it arrived in Florida, taking up semi-permanent residence inside the Neil Armstrong Operations and Checkout Building at NASA's Kennedy Space Center. Engineers and technicians will spend the next years working almost around the clock, outfitting Orion with thousands of components, and pushing the capsule through several rounds of rigorous testing as teams prepare for its flight around the moon. The first step, though, is the crew module's arrival.
When the crew module shows up here at the O&C building, it's really just a welded shell of the structure. When it gets here, we put it into a fixture called the bird cage tool, and we use that fixture to position and attach all of the mechanically attached primary and secondary structure for the crew module.
Part of that includes the heat shield, which protects the crew module as it blazes through Earth's atmosphere at astonishing speed as it returns home. Technicians with Lockheed bond those thermal protection system products onto the heat shield right here in the O&C. And they do the same for the crew module's forward bay cover.
We bond that on here, and basically this covers the forward bay of the crew module, such that once we come back into the atmosphere, this gets jettisoned and all of the landing system, i.e. parachutes, get deployed and slow the crew module down so that when it touches down in the ocean, it's only going a few miles an hour.
With the primary and secondary structures all attached, the crew module is tested to see how everything holds up. Orion is pressurized, stressing the welds to ensure they'll hold up under the proper loading. Afterwards, non-destructive evaluation of those welds is conducted to check for any voids or cracks. Once the structure is deemed strong enough, the crew module is moved just a few spaces down into the O&C's clean room for its next round of integrations.
We bring that structure into our clean room, which is you see behind me, because we need to start integrating the propulsion system and elements of the environmental control and life support subsystems, and those systems require a cleaner environment than the one we're standing in out here.
When all of that is done, the crew module is on the move again to the crew module integration station. There, all of the electrical systems, including wire harnesses and avionics boxes that control the crew module's guidance, navigation, communications, and its power subsystems, are integrated. Next, it's time to bring the spacecraft to life.
We power it up, and then we go into a whole series of functional tests to make sure all the subsystems that we've integrated up to that point are functioning properly.
But the crew module isn't the only thing that makes up the Orion spacecraft.
All the people, the work, the components that have gone into this vehicle, it's just an amazing feat.
Teams also worked closely with the European Space Agency to build the service module, the element that will power Orion on its journey around the moon. Once that arrives from Bremen, Germany, Lockheed moves forward with integrating the two.
The service module has a very similar life cycle to the crew module. We build it up structurally, we integrate the propulsion system and the other fluid systems, and then we integrate it electrically and power it up and do functional tests on it. And when we have a full service module and a full crew module, then we stack the two together and we have what's called the crew service module for Artemis 1.
Under the Artemis program, NASA plans to not only return to the moon, but to use that as a stepping stone to go farther than any human has ever gone before, Mars. To get there, it's truly a cross-country and international effort among thousands of individuals.
When you consider all the people, at the Johnson Space Center, Marshall Space Flight Center, all across the agency, SLS, Orion, the European service module, Boeing and their team, Lockheed Martin and their team, and to see all of that come together on that launch when we send it on its way to the moon, it's going to be absolutely amazing, and we're going to have a lot of really proud, happy people.
Building a spacecraft destined for deep space exploration from the ground up is no easy task. And the fact that these teams have been able to come together and do just that in the midst of a global pandemic is nothing short of amazing.
It really is a testament to the workforce. If you think about what we've been through over the years that they've been putting this together, and particularly think about the environment that this team was dealing with. We're dealing with COVID, and we're asking these folks to come into work every day and finish the spacecraft so we can keep this mission going. And we're ready, and we're excited. And so as they turn this over to us, we're ready to get going.
And really, this is only the start of Orion's path to the pad.
It's a little hard to put into words when you think about the fact that we are in the first flow of what will be our nation's deep space exploration program. It hits you in the heart, and it really speaks to why we all are doing what we're doing.